All right, now that we spent some time talking about measurement, we are now going to spend a little bit of time talking about matter in general. Chemistry is basically the study of matter, what it's made out of, how it behaves, how it interacts with other states of matter, and also we also have to take into a little bit of consideration about the energy involved in the changes in matter. So first of all, let's start with a definition of, well, what exactly is matter? Matter can be defined as anything with mass and volume. Okay, so anything that has mass and takes up some sort of space. So the question is, what is not matter? Well, that would be different forms of energy. Okay, some of the forms of energy that are very, very important in chemistry are kinetic energy and heat or thermal energy. Okay, so these are forms of heat that actually do work when it comes to chemistry. Now, there's potential energy in bonds and chemical substances. And we'll talk about that very, very briefly a little bit later on. So before we get into matter a little bit and the states of matter, let's talk a little bit about energy. Now, the law of conservation of energy has nothing to do with when we talk about, well, we're going to conserve energy. That means we want to use less energy. But the law of conservation of energy says that basically says we cannot create it or destroy it. The only thing that can happen to energy is that it can transform into a different type of energy. So kinetic energy can be transformed into heat energy, sound energy. Heat energy can be transformed back into kinetic energy. Chemical potential energy can be transformed into light energy. There's a lot of different forms of energy. Now, there is an exception to the rule that was only discovered actually recently. And that is what we call nuclear reactions. What do I mean by nuclear reaction? That's what we call a change in the nucleus or the center of an atom. These are very unusual reactions, and what they do is they actually create energy from mass. A tiny, tiny bit of mass appears to be transformed into a huge amount of energy. We see this in the atomic bombs and nuclear reactors, that type of thing. All right, so our next question is, how do we measure energy? Okay, well, the energy that we're going to be looking at is measuring heat energy. Okay, we can what we call indirectly measure. And the instrument that we use for this is a thermometer. Now you may say, what does that mean, indirectly measure? It's because most people think that that's what a thermometer does. A thermometer measures how hot or cold something is. Well, a thermometer actually measures average kinetic energy. Now, there is a relationship between kinetic energy and heat energy, but heat is basically something that moves from areas of high heat to low heat. So we can only measure heat energy when it's moving from an area of higher heat to an area of lower heat. The thermometer measures average kinetic energy, which means it's measuring the motion of the particles that make up matter. So it's measuring how fast the particles are moving. Fast-moving particles have high kinetic energy. Slow-moving particles have low kinetic energy. Now, the fact that it measures average means that it's not measuring every single particle. It's measuring where most of the particles are, but that means that there are some particles in the substance that are moving faster and some particles that are moving slower. Now, we have three basic different scales that we use. The Fahrenheit scale isn't really used that much in science. We use it when we talk about the weather. So when they tell us how hot it's going to be, so it's going to be 100 degrees outside, that's 100 degrees Fahrenheit. And it is also used in medicine. So if your mom sticks a thermometer in your mouth and says, oh, you have 102 degree fever, it's 102 degrees on the Fahrenheit scale. In science, what we use commonly is Celsius, which you may occasionally see it referred to as a centigrade scale. But we're going to call it the Celsius scale. That's the most common word for it. Okay, and that's used in scientific measurement. So when we go in the lab and we take the temperature of something, we use a Celsius thermometer. We'll talk a little bit about how hot things are on a Celsius scale versus things on a Fahrenheit scale. All right, and the very, very last scale is called the Kelvin scale. The Kelvin scale is used very commonly in some scientific calculations and formulas. That's where we'll find ourselves using the Kelvin scale. Okay, so just so you can get a feel for how are the scales related to each other. Okay, so if we have water freezing and water boiling, and let's look at the temperature that it freezes on each of the different scales. Okay, on the Fahrenheit scale, water freezes at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit. The Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So you can see, look at the difference in how many degrees between freezing and boiling on the Fahrenheit scale. Okay, there's like 180 degrees. Between the Celsius scale, it's like 100 degrees. So a degree Celsius is a lot bigger than a degree Fahrenheit. The last one is a Kelvin. Now the Kelvin scale does not have degrees. They don't call it degrees Kelvin. So this is 273 K, and water boils at 373 K, or 373 kelvins. Now what's the point of this scale? Because this is a huge number compared to water freezing at 0, water freezing at 273. Well, the Kelvin scale was developed specifically using the idea about the relationship between temperature and kinetic energy. So a man named Lord Kelvin, that was actually his name, he's a British aristocrat, theorized that, well, if the temperature went lower and lower and lower, that means that the kinetic energy was slower, the particles were moving smaller and smaller and smaller. That meant that there had to be some point which there was no kinetic energy, in which the molecules stopped moving. And he decided to call this 0 on his scale, which was called absolute 0. This is the coldest temperature of anything in space anywhere. Okay, in space comes really, really close to absolute 0. Not exactly, but very, very close. And this is the point where there is no motion of any kind. Okay, we've been trying to get to that point for a long time. 0 Kelvin, okay, where even the subatomic particles stop moving. So that would be really, really, really cold. So then let's take a look then at the relationship between energy and the three what are called common states of matter. So we're going to spend a little bit of time talking about these. You should know these. This should not be anything new. They're solid, liquid, and gas. So the first thing we're going to look at is, well, how much energy do they have as far as kinetic energy relative to each other? So a solid is a low energy state, which means that the particles in solids don't have a lot of kinetic energy. The particles in the liquids are a medium energy state, and the particles that are in the gas are a very high energy state. Well, what does their motion actually look like then? Well, in order to have a very small amount of kinetic energy and be a solid, that means that the motion is vibration in position. So if we could look at the particles in a solid, we would see they're vibrating in position. And what are they doing? And what does their position look like? They're in a 3D, what we call a crystal, which means that they're rows and columns. So they're highly organized. And they're very closely packed. Sorry, can't spell. Now, liquids then have a different motion. So if we have them vibrate faster and faster and faster, that means that they can't stay in a position. When they go from a solid to a liquid, they have to, the vibration and position has to be lost. So their motion then becomes a sliding motion. They slide past each other, which means that they lose this 3D arrangement and they become chaotic. Chaotic means there's no pattern or organization. However, they are still closely packed. It's very easy for us to actually see liquids and solids. Why? Because the particles that make up the liquid and solid matter are packed so closely together. Now, if we have these particles and they're sliding around and we tell them to go faster, slide faster and faster and faster and faster, pretty soon what's going to happen is that a couple of them are going to start breaking away from this closely packed organization. So their motion then is going to become, they're going to become free. Okay, they're going to move at high speed. And they're going to move in straight lines. So their arrangement would be far apart and very chaotic. So one of the things that you'll be challenged to do is to draw a visualization of what does this look like. If we could look at the particles in a solid, a liquid, or a gas, how would we represent their motion? What would their arrangement look like? How could we distinguish them? Now, the last thing we're going to talk about is, and this is very, very key for you to keep in mind, is that The only difference between solids, liquids, and gases is the amount of energy they have, meaning the increased amount or decreased amount of motion they have, and the type of arrangement that goes along with those motions. So if we take a cube of ice, the particles in the cube of ice, as the ice melts, are going from this type of movement to this type of movement. So this is why I'd say this, the ice is keeps its shape. Here, okay, there's no fixed organization anymore. They're sliding and moving. Okay, if we continue to heat the puddle of water here, eventually these little water particles in here will escape in the form of water in the gas form, which is called steam. Okay, and then we won't be able to see them very well. Okay, you've seen when steam rises, it seems to vanish. That's because as they're leaving there, they're starting to get farther and farther apart and zoom away in straight line motion. It's the only thing that's changing, though, is their speed. Nothing else changes. Their size doesn't change. Their composition doesn't change. So the solid to liquid transition or phase change is called melting. The liquid to gas phase change is called evaporating. Clear that up, you can't read that. Sometimes called boiling. The only difference between evaporating and boiling is evaporating is slow liquid to gas, and boiling is very rapid change from liquid to gas. And going from a solid all the way through to a gas without going to the liquid state in between, it's called subliming or sublimation. That's what dry ice does. Dry ice is carbon dioxide, okay, in the solid state. Okay, and it goes from a solid to a gas without going through liquid in between. It goes directly from here, it jumps from here to here. That's called sublimation. Now, all of these require, the melting, evaporating, and subliming require that you add energy. The particles have to move faster. Now, if we go the other direction, we have to take energy away, usually by putting it someplace where it's cold, so the energy leaves the substance and goes into the air around it. Okay, hopefully you remember this is called freezing. And the gas to liquid is called condensing. Okay, and going from a gas all the way back to a solid, okay, that's the reverse of sublimation. It's kind of a funny word. It's called deposition. You don't need to worry about too much about that. Okay, I do expect you to know that solid to liquid, the melting requires energy. Liquid to gas, evaporating or boiling, requires energy. And subliming solid to gas requires energy. Going the other way, going from a gas to a liquid or condensing requires energy be released or taken away. And going from a liquid to a solid or freezing also requires the same thing. And that's what I expect you to know about the states of matter.